Welcome to True Projects. In this video, we are going to explain about the project titled Deep Transfer Learning Strategy to Diagnose Eye-related Conditions and Diseases, an approach based on low-quality fundus images. Before diving into the execution, let me give you an overview of the project. In many emerging and underdeveloped countries, the availability of specialized healthcare professionals, especially in the field of ophthalmology, is limited. This scarcity poses a significant challenge in accurately diagnosing eye related conditions and diseases. Without access to specialists in basic health units, individuals may receive inaccurate diagnosis, which can lead to delayed treatment and increased risk of vision loss or other visual impairments. To address this critical issue, in the base paper, the author has proposed a deep transfer learning approach to diagnose eye related conditions from fundus images. Pre-trained models like VGG16, ResNet 50, Inception V3, Exception, DenseNet 121, DenseNet 169, and Inception ResNet V2 are fine tuned on a dataset of fundus images with pre processing techniques used to enhance image quality. This approach adapts knowledge from pre trained models to improve accuracy in diagnosing eye conditions, particularly from low quality images, ultimately enhancing healthcare outcomes. To further enhance performance, we have proposed object detection methods like YOLO V5 and YOLO V8 to identify diabetic retinopathy and related conditions within fundus images. These techniques pinpoint specific regions of interest, complementing classification models and potentially improving accuracy in diagnosing and treatment planning for eye related conditions. The system's effectiveness is measured using various metrics like accuracy, precision, recall, and FN score to ensure its reliability as a diagnostic tool for healthcare providers, particularly in resource limited settings. By improving the accuracy of diagnosis, it aims to prevent visual impairments or blindness through early detection and intervention, ultimately enhancing healthcare outcomes. The project aims to develop a diagnostic tool for healthcare providers in resource constrained environments, improving accuracy in diagnosing eye related conditions. Early detection and intervention facilitated by the tool have the potential to prevent visual impairments or blindness, significantly enhancing healthcare outcomes, particularly in regions with limited access to specialized care. To implement this project, we need software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Algorithms used in this project, we have done classification as well as detection. So here these are the algorithms which are used for classification, which are VGG16, ResNet 50, Inception V3, Exception, DenseNet 121, DenseNet 169, and Inception ResNet V2. And these are the algorithms which we have proposed for detection. And here the exception model outperformed the other algorithms, and that is the reason we have deployed it in the front end. And the YOLO V5 and YOLO V8 are used for detection. So let me explain you what YOLO V5 and YOLO V8 are. So here YOLO V5 is known for its speed and accuracy. YOLO V5 is implemented in PyTorch and is optimized for efficient object detection. Its focus layer reduces parameters while maintaining accuracy, making it faster and more effective in detection tasks. And coming to YOLO V8, it is the latest iteration. YOLO V8 offers higher accuracy and speed with advancements like mosaic data augmentation and anchor free detection. It comes in different sizes to cater to different application needs and computing resources. Now let us execute the project. To execute this project, first we need to open the code folder which contains the project source code files. In this project, we have utilized IPACS, Messenger, Order, and Refuge dataset. Coming to the IPACS dataset, this dataset contains fundus images of eyes captured from patients. It includes images from various eye conditions ranging from healthy eyes to those with different stages of eye diseases or abnormalities. The dataset is labeled with classes representing different conditions. So, this dataset is split into train and validation. In the training folder, we are having the different classes of IPACS dataset. So, here in the zero folder, we have the fundus images of eyes with mild diabetic retinopathy. So here all these images are used to train the models. So here in this folder we are having 6896 fundus images, and in the one folder we have the fundus images of eyes with moderate non-proliferative diabetic retinopathy. And in the two folder, we have the fundus images of eyes with no diabetic retinopathy. So here, these images contain no diabetic retinopathy. And in the three folder, we have the fundus images of eyes with proliferative diabetic retinopathy. And in the four folder, we have the fundus images of eyes with severe diabetic retinopathy. So here, these all are severe diabetic retinopathy images which are used to train the models. So all these images are used to train the models. And in the validation folder, again, we have the five classes named as 0, 1, 2, 3, 4. And in the 0 folder, we have the fundus images of eyes with mild diabetic retinopathy. And in the 1 folder, we have the fundus images of eyes with moderate non-proliferative diabetic retinopathy. And in the 2 folder, we have the fundus images of eyes with no diabetic retinopathy. And in the 3 folder, we have the fundus images of eyes with proliferate dynamic diabetic retinopathy. All these images are used to evaluate the performance. And in the 4 folder, we have the fundus images of eyes with severe diabetic retinopathy. So all these images are used to evaluate the performance. Now coming to the next data set, which is Messenger. So the Messenger dataset is a publicly available dataset of retinal images primarily focused on diabetic retinopathy. It contains fundus images obtained from diabetic patients annotated by experts to indicate the severity of diabetic retinopathy. This dataset is commonly used for training and evaluating models for diabetic retinopathy detection and classification tasks. So in this folder, again, we are having the five different classes named as 0, 1, 2, 3, 4. And in each of the folder, we have the fundus images of eyes with mild diabetic retinopathy. So here in this folder, these are the images, fundus images with mild diabetic retinopathy. And in the one folder, we again have the fundus images of eyes with moderate non-proliferative diabetic retinopathy. And in the 2, we have the fundus images of eyes with no diabetic retinopathy. And in the 3 folder, we have the fundus images of eyes with non-proliferative diabetic retinopathy. And in the 4 folder, we have the fundus images of eyes with severe diabetic retinopathy. And again, here in the output folder, it is split into train and test. So all the images from the Messenger dataset are again split into train and test. So here in the train again we are having the 5 different classes in which we have the fundus images of mild diabetic retinopathy, moderate non-proliferative diabetic retinopathy, no diabetic retinopathy, proliferate diabetic retinopathy, and severe diabetic retinopathy fundus images of eyes. So here we can see the images. So these are the fundus images of eyes with moderate non-proliferative diabetic retinopathy. Similarly, in each of the folder, we have the different classes, and all these images are used to train the models. And in the validation folder, again, we have the 5 different classes. Here, 0 is for mild diabetic retinopathy, and 1 is for moderate non-proliferative diabetic retinopathy, 2 is for no diabetic retinopathy, 3 is for proliferate diabetic retinopathy, and 4 is for severe diabetic retinopathy. So here in each of the folder, we have the fundus images of eyes with the different stages, and all these images are used to evaluate the model's performance. And in the this is the order data set. The order ocular disease intelligent recognition data set is likely a collection of fundus images encompassing various ocular diseases and conditions. It include images of conditions such as diabetic retinopathy, glaucoma, age related macular degeneration, and other eye diseases. So, in this folder, we again have test and train. And in the test folder, we are having 4 different classes named as cataract, diabetic retinopathy, glaucoma, and normal. In the cataract folder, we have the fundus images of eyes with cataract, and here in the diabetic retinopathy folder, we have the fundus images of eyes with diabetic retinopathy. And in the glaucoma folder, we have the fundus images of eyes with glaucoma. And in the normal folder, we have the fundus images of eyes which are normal. All these images are used to test the model's performance. And here in the train folder, again, we are having the 4 classes: cataract, diabetic retinopathy, glaucoma, and normal. In the cataract folder, we have the fundus images of eyes with cataract. And all these images are used to train the model. And in the diabetic retinopathy folder, we have the fundus images of eyes with diabetic retinopathy. And in the glaucoma folder, we have the fundus images of eyes with glaucoma. And here in the normal folder, we have the fundus images of eyes which are normal. All these images are used to train the models. Now coming to the next data set, which is refuge. The refuge data set or retinal fundus glaucoma challenge data set is a collection of fundus images primarily focused on glaucoma. It contains images obtained from patients with glaucoma as well as healthy individuals for comparison. So, here in this data set, this is also split into train and validation. So, in the train folder, we are having two classes named as glaucoma negative and glaucoma positive. So, in the glaucoma negative, we have the fundus images of eyes which do not contain glaucoma, that is glaucoma negative, and all these images are used to train the models. And in the glaucoma positive, we have the fundus images of eyes which contain glaucoma, that is glaucoma positive, and all these images are used to train the models. And in the validation folder, again, we have the two classes, glaucoma negative and glaucoma positive. In the glaucoma negative, we have the fundus images of eyes which do not contain glaucoma. And in the glaucoma positive, we have the fundus images of eyes which contain glaucoma. And these images are used to evaluate the performance. So, this is the sample folder in which we have the test cases. So, here in the class folder, we are having the four data sets, and in each of the data set we again have the five different classes. So here in the IPACS folder we are having the five different classes. Here 0 is mild diabetic retinopathy, and 2 is 1 is moderate non-proliferative diabetic retinopathy, 2 is no diabetic retinopathy, 3 is proliferate diabetic retinopathy, and 4 is severe diabetic retinopathy. So in each of the folder we have the fundus images of the eyes which contain that class. And coming to the Mesidor data set, again in this data set also we are having the five different classes, and in each of the folder we contain the fundus images of each class. And again in the order data set, we have the four classes, cataract, diabetic retinopathy, glaucoma, and normal. And in each of the folder, we have the fundus eye images for that particular class. And coming to the refuge data set, in this data set, we are having two classes, glaucoma negative and glaucoma positive. And in each of the folder, we have the fundus images for the respective class. So these are the test cases which we will use during the execution in the front end. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. So here, this is the YOLO folder which contains the images for detection. Along with the images, we even have the labels for those images, which provides details about the object's location and classes within the image. And these are notebook.ipynb files. These Jupyter notebook files, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. And here, these are the model files which contain algorithm information which will be loaded into the project code during runtime. First, we need to copy the path of the code folder from the address bar of the file explorer. Here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have registered, which are static, and then click on sign in. We have logged in successfully and we are redirected to the production page. Now click on classification link here. So here we can see the 4 data sets which are IPACS, Messenger, Odor and Refuge. First, we will execute the project using the IPACS data set. So click on IPACS. So here we need to upload the fundus images of the eyes, and after uploading the images, the application will predict the stage of the disease. Click on choose file. So here from the test cases folder, from the IPACS dataset, I'm selecting the first class. From that, I'm selecting this image. Now click on upload button. This is the uploaded image and it is predicted as mild DIA, that is mild diabetic retinopathy. So it is non-proliferative diabetic retinopathy, NPDR. It is the early stage of the disease in which symptoms will be mild or non-existent. Let us upload some more images. Click on classification link and then click on IPACS dataset. Click on choose file. So from the IPACS dataset, from the one folder, I'm selecting this image. Now click on open. Click on upload button. So here, this is the uploaded image and it is predicted as moderate non-proliferative diabetic retinopathy. The tiny blood vessels further swell up, blocking blood flow to the retina and preventing proper nourishment. Let us upload some more images. Click on classification link, click on IPACS. So again from the IPACS dataset, from the two folder, that is which contains non-diabetic fundus eye images, I'm selecting this image. Click on open. Now click on upload button. So here this is the uploaded image and it is predicted as no diabetic retinopathy. So it is a normal fundus image which do not contain diabetic retinopathy. Click on classification link again. Click on IPACS dataset. So again from the IPACS dataset, I am selecting the image from the third folder. So this is the uploaded image and it is predicted as proliferative diabetic retinopathy. Is the advanced stage where abnormal new blood vessels grow on the surface of the retina. So it is the advanced stage. Let us upload some more images. Click on classification link. Click on IPACS dataset. So now we will upload a image from the fourth folder, which contains the fundus images of eyes with severe diabetic retinopathy. So here I'm selecting this image. Click on open. Now click on upload button. So this is the uploaded image and it is predicted as severe diabetic retinopathy. Severe diabetic retinopathy is an eye condition that can cause vision loss and blindness in people who have diabetes. So, due to this, people can have blindness and can lose the vision. Let us upload some more images. Click on classification link. Now let us execute the project using the second data set, which is Misidor. So click on it. So here we need to upload the images. So click on choose file. So from the sample test cases, from the Misidor data set, and from the zero folder, which is mild diabetic retinopathy, I'm selecting the second image. Now click on upload button. So here, this is the uploaded image and it is predicted as mild diabetic retinopathy. So it is non-proliferative diabetic retinopathy is the early stage of the disease in which symptoms will be mild or non-existent. So in this, it is the early stage and the symptoms will be mild. Let us upload some more images. Click on classification link. Again, click on method or data set. Choose file. So from the message door, from the one folder which contains the fundus images of moderate non-proliferative diabetic retinopathy, I'm selecting this image. Click on upload. So here, this is the uploaded image and it is predicted as moderate non-proliferative diabetic retinopathy. The tiny blood vessels further swell up, blocking blood flow to the retina and preventing proper nourishment. So this is the second stage, we can say. Let us upload some more images. So click on classification link, click on messy door, choose file. So from the two folder, which contains no diabetic retinopathy fundus eye images, I'm selecting this image. Click on upload button. So here, this is the uploaded image and it is predicted as no diabetic retinopathy. So it is a normal fundus image. Click on classification link again, click on Messidor, choose file. So from the sample test cases, from the Messidor data set, from the third folder, which contains the proliferative diabetic retinopathy fundus eye images, I'm selecting this image. Click on upload. So here, this is the uploaded image and it is predicted as proliferate diabetic retinopathy. So it is the advanced stage where abnormal new blood vessels grow on the surface of the retina. Let us upload some more images from the Messidor data itself. Click on choose file. So from the test cases from the fourth folder, which contains the fundus eye images of severe diabetic retinopathy, I'm selecting this image. Click on upload. So this is the uploaded image and it is predicted as severe diabetic retinopathy. Severe diabetic retinopathy is an eye condition that can cause people vision loss and blindness in people who have diabetes. So the people who are having diabetes, for them, it can cause vision loss and blindness. That is severe diabetic retinopathy. Now let us upload some more images. Click on classification link. Now we will execute the project using the ordered data set. So click on it. Click on choose file. So from the sample test cases, from the ordered data set, so here the ordered data set is having these four classes. So from the cataract folder, I'm selecting this image. Click on upload. So this is the uploaded image and it is predicted as cataract. A cataract is a clouding of the lens of the eye. This is an area that is normally clear. The retina is a tissue lining that is sensitive to light. Let us upload some more images. Click on classification link. Then click on ordered dataset. Choose file. So from the ordered dataset, from the diabetic retinopathy folder, I'm selecting this image. Click on upload. So this is the uploaded fundus eye image, and it is predicted as diabetic retinopathy. Diabetic retinopathy is caused by damage to the blood vessels in the tissue at the back of the eye retina. So here, this person is having diabetic retinopathy. Click on classification link, click on order data set, choose file. So from the order data set, from the glaucoma folder, I'm selecting this image, click on upload. So this is the uploaded fundus eye image, and it is predicted as glaucoma. Glaucoma is a group of eye diseases that can cause vision loss and blindness by damaging a nerve in the back of your eye called the optic nerve. So glaucoma is caused due to the damage of the optic nerve. Click on classification link, click on ordered data set, click on choose file. From the ordered data set, from the normal folder, I'm selecting this image. Click on upload. So here, this is the uploaded fundus eye image, and it is predicted as normal. That is, no diabetic retinopathy. This means that the person is not suffering with the diabetic retinopathy and it is completely normal. Now let us execute the project using the fourth data set, which is refuge. So click on it, choose file. So from the sample test cases, from the refuge data set, from the glaucoma negative folder, I'm selecting this image. So here, these are the images of fundus eye which do not contain glaucoma. Open, click on upload. So this is the uploaded image, and it is predicted as glaucoma negative. This means that the person is not having glaucoma. Again, click on classification link, click on refuge dataset, click on choose file. So from the refuge dataset, I'm selecting this image from the glaucoma positive. Now click on upload button. So here, this is the uploaded image, and it is predicted as glaucoma, that is glaucoma positive. So glaucoma is a group of eye diseases that can cause vision loss and blindness by damaging the nerve in the back of your eye called the optic nerve. So if the optic nerve is damaged, then the person can have glaucoma. So in this way, just by uploading the fundus images of eye, we can predict the different stages of the eye diseases. Now click on detection link. We will do the detection using these three data sets, which are IPAX, odor, and refuge. Now click on IPAX dataset. Click on choose file. So again, from the test cases folder, from the detect folder, we have these three data sets here. So from the IPAX data set, so here these are the test cases for detection. So here I'm selecting this image. Now click on open. Now click on upload button. So here this is the uploaded image. So here we can see that this fundus eye image is detected as normal. And here we can see the probability score, which tells us the confidence level of the image for the detection. Let us upload some more images. Click on choose file. So here from the IPACS dataset, I'm selecting this image. Now click on open. So here we can see that the image is loaded. Now click on upload button. So here we can see that this fungicide image is detected as moderate. And here we have the probability score, which tells us the confidence level for detection. Let us upload some more images. Let us upload the images from the order dataset. So click on order. Now click on choose file. So here from the detection, from the order dataset, I'm selecting the first image. Click on open. Now click on upload button. So here we can see this is the uploaded fundus eye image and it is detected as cataract with 0.81 probability score. So here it tells us the confidence level for detection. Let us upload some more images. Click on detection link, click on order dataset, click on choose file. So again from the order dataset, I'm selecting this image, click on open. Now click on upload button. So here this is the uploaded fundus image and it is detected as glaucoma. And here we can see the probability score, which is 0.94, which tells us a confidence level for the detection. So let us upload the images from the refuge dataset. So click on refuge. Click on choose file. So here from the detection, from the refuge folder, I'm selecting this image, click on open. So the image is loaded and here we can see it is detected as glaucoma negative. And this is the detected bounding box. Let us upload some more images. Click on detection, click on refuge dataset, click on choose file. So from the refuge dataset, I'm selecting this image. So here we can see that the image is loaded and this is the uploaded image and it is detected as glaucoma positive. So in this way, just by uploading the fungicide images, we can detect the types of the diabetic retinopathy. Now click on graph link here. So here we are having the graphs for all the 4 data sets, IPACS, Messidor, Oder, and Refuge. Click on IPACS dataset. So here we have the loss and accuracy curve of exception. So here for every increasing epoch, loss is decreasing in both training and validation. And here for every increasing epoch, accuracy is increasing in both training and validation. And here we have the comparison graphs for the different evaluation metrics, accuracy, precision, and recall. On the x-axis, we have the score for the different evaluation metrics. And on the y-axis, we have the algorithm name. So the algorithm which is performing best will be used for prediction. So here the exception model outperformed the other algorithms and that is the reason we have deployed it in the front end. And here this is the confusion matrix for the detection and this is the precision recall curve. This is the F1 confidence curve and here we have the performance evaluation metrics comparison graphs for the detection models, that is for the YOLO models. So this is the MAP comparison graph. This is a precision comparison graph and here this is the recall comparison graph. Now click on graph link again. Let us see the graphs for the Messidor dataset. So click on it. So here we have the loss and accuracy curve of exception. So here for every increasing epoch, loss is decreasing in both training and validation. And here for every increasing epoch, accuracy is increasing in both training and validation. And here we have the comparison graphs for the different evaluation metrics: accuracy, precision, and recall. So on the x-axis, we have the score for the different evaluation metrics, and on the y-axis, we have the algorithm name. And this is the confusion matrix for the detection, and this is the precision recall curve, and this is the F1 confidence curve. And here we have the comparison graphs for the detection model, MAP score, precision score, and recall score. Now again, click on graph link. Let us see the graphs for the order data set. So click on it. So here, these are the loss and accuracy curve of exception. Here for every increasing epoch, loss is decreasing in both training and validation. And here for every increasing epoch, accuracy is also increasing in both training and validation. And these are the comparison graphs for the different evaluation metrics: accuracy, precision, and recall. On the x-axis, we have the score for the different evaluation metrics, and on the y-axis, we have the algorithm name. And here, this is the confusion matrix for detection, and this is the precision recall curve. And here, this is the F1 confidence curve. And these are the comparison graphs for the detection models, which are MAP score, precision score, and recall score. On the x-axis, we have the score for the different evaluation metrics, and on the y-axis, we have the algorithm name. Now again, click on graph link. Let us see the graphs for the refuge data set. So click on it. So here, these are the loss and accuracy curve of exception. So here we can see for every increasing epoch, loss is decreasing in both training and validation. And here for every increasing epoch, accuracy is also increasing in both training and validation. These are the comparison graphs. And here, this is the confusion matrix for detection. And this is the precision recall curve. This is the F1 confidence curve. And here we have the comparison graphs for the detection models. On the x-axis, we have the score, and on the y-axis, we have the algorithm name. Now click on sign out button here. So in this project, we aim to prevent visual impairments or blindness through early detection and intervention, ultimately enhancing healthcare outcomes.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.